So in this video, we're going to look at how Taylor polynomials are going to help us make approximations to functions. And so we're going to start out with just looking at what happens if we calculate the Taylor polynomial and then start adding term by term how that affects our approximations sort of visually. And then we will look again at making our error estimates. So we're going to start with an example involving cosine of x. And so this is what our standard graph of cosine of x looks like. And we're going to generate the Maclaurin series, the Maclaurin polynomial for the cosine function centered at 0, and we're going to do the approximation there. So we're going to try to approximate this curve starting at this point. And so when we actually generate the formula, the very first term for this even function is the constant 1. So this is a zoom in on our cosine function. We have our peak, and this is the first term in the series. And you can see it's the exact value of the function at the center, but the further away that you get from that point, the worse the approximation becomes. It's not bad if you stay nearby, but the further away you get, the worse it gets, which is what you'd expect from an approximation. So let's add in a second term. Now, if we add in a second term, here the blue line is our 1, and the black line is our 2-term cosine approximation. This is our quadratic approximation. And again, you can see that it does deviate eventually from the path of the cosine function, but is staying much closer, much further away than it was before. So it's doing a better job with the approximation for a longer stretch of time, which would mean that even at this point, it's closer in terms of its error. So even though the 1 was still pretty good, the polynomial with the x squared term will be better in terms of making an estimate. Now, if we add additional terms, we can see that, again, there's our 1, then our quadratic is this purple line now, and then if we add additional terms, again, they're all even functions because cosine is an even function, but you're going to get better and better approximations. So this green line here is the x to the 4th term, and then this black line here is our x to the 6th term. You can see it goes out even further, staying closer and closer to this red line, which is our cosine function. And so as you keep adding additional terms, you will keep getting better and better approximations that will stay pretty good longer and longer and longer. Now, what happens if I want to know, like, how many terms should I use to do my approximation? At a particular, and the question is always, how many terms do you need to do the approximation at a particular point? So notice now I've gone up to the degree 10 polynomial. That's my black line right here. And it's, again, doing a much better job longer and longer and longer to this curve. So how far do I have to go? How many terms do I need? That's going to depend in part on the size of the error that I want, and it's going to depend on how far away the point I'm doing the estimate at is from my center. And I can keep going. I can keep adding additional terms, and the more that you add, the longer it will stay very close to the function that you're doing the approximation of. Eventually, it will deviate if you stop adding additional terms. Now, we can also look at other kinds of functions. So like the inverse tangent function is going to behave very similarly. Here, I'm working not with a Maclaurin polynomial, but I'm working with a Taylor polynomial centered at 1. And we can see that even though I have a value for my first term, The estimate is not very good. It's adequate, but only very, very, very close to the actual value. It's much worse with just the constant than it was with the cosine function. But you can see that as soon as I add my linear term, now I stay close to this curve even better. That's essentially our first order linear approximation that we would have done from way back when in Calc 1. But if I add a polynomial term to it, a quadratic term, again, I'm staying closer for further. Now, I'm actually doing a better job on the left side than the right side for graphs that are not, where I'm not dealing with a perfectly symmetric graph, or I'm centering them from one side of the symmetry rather than the other. This is a very common thing that will happen, is that you will get approximations that are better farther on one side than on the other. Exponentials do this a lot. And again, as you keep adding terms, it will stay close to our function curve longer on both sides, but in particular, on this particular graph, it will do better longer on the left side, just because of the way the function is. Now, what if I want to approximate this error, the value of the function at a particular point, not at the center? How can I do that? Well, the way that we're going to calculate that, of course, is the error term based on where I stop. So if I'm using, say, a fourth degree polynomial, then my error term on the fourth degree is going to depend on the fifth derivative. And recall from a previous video, we mentioned that this term, this f to the n plus 1 derivative at z, is actually just a notation that some textbooks use to indicate that we're looking for the maximum value on some interval that contains both the center and the point where we're doing our estimate. Now, the inverse tangent function itself has a maximum value on that interval, which is the absolute value is pi over 2, but its derivative doesn't necessarily have that same maximum value. So what you would have to do is you would have to calculate that fifth derivative, and then you would have to find out what the maximum value on the interval in question is. Now, if you're trying to estimate at 0.5 and negative 0.5, then you can use that as your interval. These are, your interval should contain the center and they should contain the point. So if you're estimating the Taylor polynomial for inverse tangent at 0, then you can use the interval negative 1/2 to 1/2. If you're centering it at 1, then you would not be able to use the negative 1/2 to 1/2 interval, because 1 is not even inside that interval. You could use different intervals for these two estimates, or widen it out to include the interval that it contains both endpoints. But we saw that the errors are not really symmetric when you're centering it at 1. And so using two different estimates would probably be a good idea. Now, for the cosine function or the sine function, we know that the derivatives are always sine and cosine, and the maximum on any sine and cosine function is always just 1 or negative 1. And so the absolute value would just be 1, and that makes our formula much simpler. And for those kinds of scenarios, again, you would have to come up with an expression. If the derivative does depend on x, you would have to find that appropriate derivative, and then again find the maximum on the given interval instead of using 1 for sine and cosine, which is much easier. But you would have a value here, and then you would have to find again, you're trying to estimate how many terms do you need to know what n is to get the desired error that you want. And so what you're going to have to do is you're going to have to choose a point where you're estimating it. So for instance, if you're estimating it centered at 0 at -1 radians, you would place your -1 in here, and then you would have an expression that depended only on n. The absolute value will throw away the negative part, and the 1 to the n will throw away, and 1 to the n plus 1 will also, 1 to any power is 1. And so you're basically just left with 1 over this n plus 1 factorial. And you can then put that in a table of values. This is not a nice, easy function to do an estimate with. And so you would just figure out how many terms, how many n's do you need until you get n plus 1 factorial to be greater than the reciprocal of this value, or 1 over n plus 1 factorial to be less than 0.0001. If you have a more complicated expression, such as for the exponential approximation that we did in a prior video, now at this point, then you can just build a table for these e's, because every one of these e minus 1 to the n plus 1 is going to differ each time. And so it's better, there's no way that you can algebraically manipulate this in order to solve it, because you have n in more than one places, you have n factorial. So you can build a table of your estimates for the error and then figure out where that error falls below the desired value. And again, kind of keep in mind, if you're looking for 0.0001, 0.00015 is too large, which means that you would need to go down to the next term. So finding the number of terms that you need can be a little challenging, but essentially you're going to use the general formula for the error, and then you're going to figure out, once you figure out that maximum value on your interval, where how many terms you're going to need in order to do that estimate. Sometimes the trickiest thing is figuring out what interval you need in order to do this analysis.